In the context of machine learning model defense, particularly against collusion attacks, this research proposes a novel strategy based on adaptive attractors. Existing methods using attractor-based rewriters are vulnerable to collusion attacks as they do not effectively mislead colluders. The authors formulate the problem, conduct empirical studies, and propose using adaptive attractors with a U-shaped weight curve to dynamically adjust the weight of the attractors based on the proximity of an input sample to the decision boundary. Experimental results demonstrate a significant reduction in the attack success rate, converging to around 15% even with a large number of copies for collusion. This approach builds upon parameter rewriting and introduces a flexible weight mechanism guided by a U-shaped curve, enhancing resilience against both single-copy replication and multi-copy collusion attacks. The research focuses on local properties and the concept of attractors, extending previous works on score-based black box settings and preprocessing methods. It provides formulations to estimate the effectiveness of collusion attacks and conduct simulations to compare with actual success rates, aiming to understand replication attack characteristics and identify areas for defense strategy improvement. The research paper discusses a defense strategy against machine learning adversarial collusion attacks. It presents two approaches: copies obtained through summation with rewriters and copies obtained through embedded attractors. The first formulation defines a random variable C as a weighted sum of the original copy and a random variable re, with the success rate calculated as the probability that C lies in the interval t infinity. The second formulation constructs an alternative approach based on the motivation that each copy has different adversarial regions. The original model is represented as a set of tuples, and a copy issued to a buyer is embedded with an attractor I. Both formulations utilize the Monte Carlo method for simulation. The results show that the actual performance of attractor-based rewriting is consistent with the simulation results. The study suggests developing a parameter rewriting method that surpasses the original attractor-based rewriter's performance. It also analyzes the shift in each component of a copy under attack, indicating that the attack concentrates on one component, mostly on the original model or the attractor component. The paper addresses the vulnerability of machine learning models to adversarial attacks, particularly collusion attacks where an adversary utilizes multiple copies of the original model to enhance the attack's effectiveness. To mitigate such attacks, the authors propose a novel approach employing adaptive attractors, which are strategically placed in the input space to influence the output of the model. The proposed method introduces a flexible alpha value that follows a U-shaped curve, reflecting the relationship between the distance to the decision boundary and the weightage of attractors added to the model. For samples far away from the decision boundary, the authors derive a value for the weight of the rewriter, ensuring that the predicted class for the combined model is about to flip from the prediction made by the original model. This value, denoted as micro, is computed by solving an equation that minimizes the gap between the highest score and the second highest in the original classifier to 0. A small value, e, is then subtracted from micro to obtain the final alpha value. For samples near the decision boundary, the weightage of attractors is chosen empirically. In the example provided, the authors set the weightage to a specific value to achieve the desired effect. The adaptive attractors approach aims to maintain the effectiveness of the parameter rewriting at a constant level, regardless of the number of copies available to the adversary. This approach exploits the iterative nature of attacks, guiding them to move closer to a nearby attractor and potentially causing the attack to move in circles and fail to converge within a reasonable number of iterations. The authors also discuss potential areas for improvement, including enhancing the influence of attractors near and far away from the decision boundary. The adaptive attractors approach is designed to provide a robust defense strategy against ML adversarial collusion attacks, addressing the limitations and vulnerabilities of existing methods. In the evaluation setup, the authors used two distinct datasets, CIFAR10 and GTSRB. The CIFAR10 dataset consists of a diverse range of images, including animals and vehicles, with 50,000 training images and 10,000 testing images. The GTSRB dataset focuses on traffic signs and includes 43 different classes, with 39,209 training images and 12,630 testing images. The authors resize all images to dimensions of 32 × 32 × 3 to ensure consistency. The proposed defense strategy is tested on both datasets, demonstrating its effectiveness in mitigating collusion attacks. The authors analyze the shift in each component of a copy under attack, using the flexible alpha approach. The results show that the attack is less likely to succeed, with fewer points in the figure indicating fewer samples becoming adversarial. For successful samples, the shift in scores forms two clusters, with the dominant part of the score change contributed by the attractor-based rewriter. The authors further observe that the shift no longer varies much with the increasing number of copies in the collusion attack, suggesting that the flexible alpha approach is more resistant to collusion attacks. This is illustrated in Figure 4, which shows the shift caused by increasing the number of colluding copies, with the positions of the peaks on the horizontal axis remaining the same. In the realm of machine learning, a significant challenge arises in the form of collusion attacks, which exploit the distributed nature of model copies to launch stronger adversarial attacks. The existing state-of-the-art approach utilizes parameter rewriting with an attractor-based rewriter to distribute copies with different attractors, resulting in non-replicable adversarial samples across copies. However, this method is limited when multiple buyers collude to launch attacks, as the collusion attack proves much stronger than independent attacks. To address this limitation, the proposed method introduces the utilization of adaptive attractors guided by a U-shaped curve. This approach overcomes the limitations of the existing method and improves resilience against collusion attacks. The performance of the new approach is evaluated under custom and boundary collusion attacks, using the CIFAR10 and GTSRB datasets. The results demonstrate the superior performance of the new approach in the face of collusion attacks, with the attack success rate converging to approximately 15% even when 40 copies are employed for collusion. In contrast, the attack success rate for the original attractor-based rewriter exhibits unbounded growth with the number of colluding copies. Similarly, under the modified boundary attack, the new method shows a much more gradual increase in attack success rate compared to the original attractor-based rewriter. The findings underscore the potential of attractor-based defenses and the importance of adaptively injecting attractors according to each input sample. Future research directions include exploring further advancements in adaptive attractors, such as employing a machine learning algorithm to control the injection of each individual hole and bump. This paper concludes by highlighting the significance of addressing collusion attacks in the cell-buyer distribution setting of machine learning models and emphasizing the need for continued innovation in attractor-based defenses. The research paper discusses the pressing issue of adversarial attacks on machine learning models, particularly focusing on collusion attacks. It provides a comprehensive review of existing defenses and proposes a novel strategy involving attractors, distributed models, and statistical detection. Attractors are designed to confuse and detect adversarial attacks by leveraging the inherent properties of neural networks. Distributing different copies of the model to various users reduces the effectiveness of attacks by introducing variability. Statistical detection analyzes input properties to identify potential threats. The paper concludes by emphasizing the need for continuous innovation in adversarial attack mitigation, highlighting the ongoing arms race between attackers and defenders.